SwayamPrabha. Digital India. Educated India.
Welcome back. So let's continue the discussion on different combustion modeling approach, and they are theoretical as well as the numerical point of view. So what we have done so far, we have looked at the simple models, like started with AD breakup model, then AD dissipation model, and then followed by the discussion on AD dissipation concept model, and then we have looked at the statistical based model like transported PDF. So now we will move to the next set of discussion, which will be specific or rather more applicable to the premixed combustion, and that context we will discuss about some of these premixed combustion based model. So what we have done so far, we have discussed this part which are applicable to any mode of combustion, though I have already mentioned anything applicable means does not become it is going to be accurate enough, but they can be theoretically applied to any sort of model with their pros and cons. Now these set of models are very specific to the premixed combustion, then we will go to the non-premixed combustion. So just to quickly look at a freely propagating premixed flame, this is what we, so your reactant comes in, these are the product, and this is going to be reaction zone where your chemical reaction takes place. Because of that there would be heat release and there will be density change and the flow accelerate. One of the very fundamental property of the premixed flame is their flame velocity or laminar flame velocity and or laminar burning speed, or the second one is the flame thickness. So if you just recall, this laminar flame speed or laminar burning velocity proportional to the diffusivity and also the chemical time scale. So now for this freely propagating system, this will be one dimensional premixed flame. So we have our continuity equation, where then we write the species mass fraction equation, where this is the chemical source term, as we have seen it so many times, chemical source term, and then we write the temperature equation. This is specifically for this freely propagating flame, which with the assumption that remains one dimensional in variation. So we write the temperature equation there, and then to close down this all these above equation, we require equation of state where pressure density are coupled, and then the enthalpy, which has a enthalpy of formation and the other part. So now one of the thing which is required is the diffusivity of the species. For the time being, we will assume the constant Lewis number model. So that means Lewis number is 1. Typically if you look at that for different species, this is how the variation of the Lewis number. And now once you assume the Lewis number 1, so that means your thermal diffusion and mass diffusion, they will be of the same order. So we will use the fixed law of diffusion, which we write in terms of gradient, and then we get the relationship between lambda and Cp, which is in temperature dependency there. Now we convert the temperature equation, and then we can see there is a, if we plot these things for different term, in the reaction zone there is always a balance between convection and conduction. That means this is the term and this term, and reaction zone, this should be, I mean this is preheat zone, and this side is the reaction zone. So this is a balance between reaction, conduction and convection, and these are the different terms what you can plot and see how they actually vary from one zone to another zone. So, this picture we have seen it, what happens in a turbulent flame front. You see lot of wrinkles like this, and this is because of your eddies, and these eddies can basically allow this flame surface to wrinkle like that. So, this turbulence chemistry leading to increase of flame surface, so increase of conversion, that means heat release will increase, flame front disruption. So, that this will not only increase the surface when there is increase in the surface, volumetric heat release will increase, at the same time there could be some disruption of the flame front. Now, just to quick recap of this is how one can see the structure of premixed flames. I mean, these are turbulent premixed flame, and you can see different kind of structure. All these wrinkled or the curved wrinkled shape is primarily due to eddies of different scale, which could be starting from the large scale to small scale. So, multiple scale that would form that. Now, if you look at the instantaneous images, this is the instantaneous flame front what you can see, and if you put that flame brush, this is what one can see. I mean, this is the flame brush, and in between there would be lot of this chaotic randomness. So, one is that definition of the flame thickness, which is proportional to alpha by SL. One can write in terms of diffusivity and the flame speed, Smith number which is 1, Lewis number 1, Prandtl number 1, these are the non-dimensional number. Now, there would be one important definition which is required is the turbulent Reynolds number, which turbulence Reynolds number is defined as u prime lambda by nu, where lambda is the integral length scale of the turbulence. So, the turbulent Damköhler number will be ratio of the flow time scale to chemical time scale. So, this will dictate which one is dominating, whether the flow is dominating or the kinetics is dominating. So, depending on that, so the Damköhler number would play an important role, and one can distinguish different flame zones through that. Some time scale, the flow time scale would be of lambda by u prime, because this is our integral length scale. Characteristics time scale is del S by SL. So, the Damköhler number one can put it, it is a ratio of flow chemical to chemical time scale. So, once you put that, this is what you get in. And this lambda, if we now use the Taylor microscale and Kolmogorov length scale, we can use that thing to define the Karlov's number, which is the ratio of lambda by eta. So, one can write in terms of Taylor microscale and the fluctuating component of these things. So, the Reynolds number based on lambda would be u prime lambda, this is Reynolds number based on lambda, and turbulent Reynolds number based on eta would be u prime eta nu. So, if you look at the ratio between this Re lambda, Re inverted lambda, Re Taylor at the Taylor length scale Re lambda square, this would be Re eta to the power 4. So, this is an important correlation, one can think up that how the scales changes. Now, when there is a premixed flame front, one thing that will happen now, you will get one more important thing is that we have seen, instead of laminar burn, I mean top of the laminar burning velocity, you get turbulent burning velocity. So, turbulent burning velocity, so this depends on the local mean properties, that is one of the important thing, but there is no consensus in literature whether the burning velocity is a characteristics quantity that can be defined unambiguously for different geometries. So, that is another important point, that means flame structure changes, and the flame structure is also dependent on your turbulent scale, length scale and time scale. Now, turbulent length scale will also, large scale structure depends on the geometry. So, the large scale structure will react to the impact or would impact to the flame front differently compared to a different length scale, and the flame surface deformation would be different. So, that way these things are not very unique. Then, so this was proposed by Damkohler. So, there are magnitude of the scale and then these things. So, we can have wrinkle frame or purely kinematically controlled frame. This is a simple structure where you have a flame front. This is your unburned mixture and this is the burned mixture. So, the laminar flame velocity move like this, and if I take this surface, this is how the turbulent flame front would be acting. So, through the equating the mass flux through the instantaneous turbulent flame surface area. So, where we can write m dot equals to rho unburned SL AT equals to rho unburned ST A naught. So, we are equating the mass flux whatever coming in, that is going out, and using that we are writing that. So, ST by SL is somewhere proportionate to the ratio, area ratio. Now, using the geometric approximation, Damkohler proposed that this should be 1 plus u prime by, so this is an initial one, and then ST by SL would be 1 plus u prime by SL. So, this is a very important correlation. Initial days people have used it extensively, but later on there are modifications which are proposed to this kind of correlations, and one can also, like Skelkin showed that this is not the linear variation of u prime by SL, it is something like this. So, that is what, and relationship proposed by Klimov is something different, which is like this. So, if you use different ratio of ST by SL, the impact on the frame front would be also different. So, these are the proposition that was made. Then later on Clavin and Williams proposed that no, ST by SL would be of different order. So, it is a slightly more complicated, and Goulder proposed that this would be of this order. So, there are, if you look at the literature, I mean not only the textbook, also the scientific reports and journals, you can see that there are plenty of these kind of things which are proposed, and every correlation has its own advantage or disadvantage, or rather proposed based on some set of observations or database which was collected through the, what it essentially means that ST by SL proportional to diffusivity, turbulent diffusivity and the molecular diffusivity. So, we can using that, but the turbulent diffusivity is proportional to this and molecular diffusivity. So, we can say that ST by SL would be proportional to like that. Now, if you have a small intensity turbulence condition, there are not many formulation available. So, in this case the turbulent mixing is rapid as compared to the chemistry. So, and the distributed reaction zone, Goulder in 1990 proposed that this ratio would be ST by SL is 6.4 into SL by U prime 3 by 4. So, as I said, there are multiple of these, but the situation is that the statement of or the correlation of turbulent burning velocity is not universal or uniform. So, you require numerical simulation plot. I mean that is why using flamelet model, turbulent burning closure, graded numerical simulation, these are the things one has to do or look at the, and typically the experimental measurement methods, they look at the conical stationary flames, swelling flames and all these things where. So, now if you look at the method of analysis, now one way would be it is a flame normal analysis where you gather the information in the direction to the flame surface, or you can use the one point analysis. So, the flamelet based model, these will be the flame normal kind of analysis where you have a fresh gas and burned gas, and the PDM models are essentially the one point analysis. So, when you do the flame normal analysis, there one important variable which is shown is that progress variable C, which is typically in fresh gas 1, and when it is the burned gas it is 0 and burned gas it is 1. So, this progress variable says that it is monotonously increasing from reactants to product side, and it is normalized between 0 and 1. So, it could be defined in terms of species mass fraction or temperature like that. Now, in flamelet model, in turbulent calculations, the transport equation of the progress variable is solved. So, that means along with our mass momentum, turbulence, kinetic turbulence. We solve also progress variable, and then use the other information from the lookup table and all this we can solve for the rest of the things. Now we can typically for the premix flame there are different regimens one can. So if you look at a simple one flame front, which is a reactant this side and product, this is our laminar burning velocity, this is the flame thickness. So U prime by SL is our RMS fluctuation to speed, LT by is the integral length scale to delta L. So this is our tau k or tau L would be like that, chemical time scale would be like this. So there are some other scales. One is the, you can have mean flow scale where length scale is L, velocity U, time is this, integral scale L naught, so velocity would be and the time naught would be, and colmograph scale it would be this, and there you have flame speed, flame thickness and all this. So this is again important. We come back to this structure where your flow scale will be like this, and then your chemical time scale is delta by SL0. So you need this to be connected with this non-dimensional like a turbulence Reynolds number, Damkohler number, or Karlovich number. So the chemical time step and the flow time scale they are sort of. Now some interpretation, you can have a, let us say, a planar flame where uniform flow field is coming in like this. So this would be our SL, this is a planar flame. So planar flame for the stability criteria is U has to be SL. Then if you have, let us say, wrinkled flame, this is our flame front, I mean the upcoming flow field which is coming at U, this is wrinkled flame and this is our SL. So which is nothing but one can actually say the equivalence is that you have some eddies like this, small eddies which is interacting, and then plus you have some flow. So there is a combination of this. So these are our eddies. So this combination can give you this scale. So your, let us say if you have a situation like this where this is the size and this is the length of the eddy L and this is my UL, this is unburned and burnt side, then our eddy size is L, eddy velocity would be UL, then turnover time would be eddy, turnover time TAD is L by UL. So the mixing time would be T mixing, which would be LK by UK. Then we can find out this TAD by T mixing is REL to the power half, where LK is eta and UK is U eta. That means the Kolmogorov length scale. Now you can have this kind of a schematic like small structure to this goes to small and this goes to. So you have a inlet, then this is your energy transfer. This already we have discussed in details at epsilon, and this is in terms of heat. So if you say this is my demarcation zone and this is my eddy size L, this would be my delta L, that means the reaction zone. So one can define the scale relationship among the scales, like we can have epsilon, which we have already seen, which would be finally V naught cube by L naught, which is V eta cube by eta. So finally tau naught by tau eta is proportional to L naught by eta to the power 2/3. Similarly, V eta by nu is 1, which will give us V naught L naught V eta proportional to Re by L naught. Similarly, L naught by eta would be proportional to L naught by nu V naught eta by L naught 1/3. So that means L naught by eta proportional to Re L naught to the power 3/4, V naught by V eta, which is Re L naught to the power 1/4, and tau naught by tau eta, Re L naught to the power half. So this relationship, anyway, this is a recapitulation, because in the turbulent discussion we have done that. So our Re L naught is nothing but V naught L naught by nu. Damp-Coulomb number would be tau naught by tau c, which is L naught by V naught SL by delta L. Karlovich number is tau c by tau eta, which is delta L by SL, V eta by eta, delta L by SL delta L, d by nu V eta by eta, which is delta L by eta square. And turbulent intensity, that would be Ti, which is V naught by SL. So using this different number or non-dimensional numbers, one can define this diagram, which is called the Borghi diagram. It defines the different this is a laminar flame, then you can have wrinkle flamelets. So this side you go LT by delta L, and this side you go U prime by UL. This is a line which is Karlovich number less than 1 corrugated flamelet regime. This is distributed reaction regime, and this is well star, where the Damp-Coulomb number less than 1, and this line correspond to Damp-Coulomb number 1. And this particular zone, you have both Damp-Coulomb number and Karlovich number greater than 1. Then later on it was modified by Peters, and it is a slight modification to that to see. So as I said, this is a laminar zone, this remains a wrinkle flamelet, then this region they say it is a corrugated flamelet, then this line correspond to Karlovich number 1, so this is thin reaction zone, and this is the, so most of the flame front will lie in this zone, and this is our broken reaction zone and all this. Because once you have a information about your geometry and your fuel and the compositions, one can estimate where this flame is going to actually belong. Now once you come to flamelet regime, your Karlovich number is getting that del L by SL V eta by eta, which is going to be del L by eta square, which is less than 1. So that means if I plot a diagram where this is my, let us say, flame front, and this is the AD which is actually going to act on it, this is unburned side, this is burned side. So the thickness of the reaction zone plus, I can say this is reaction plus preheat zone, the thickness of the reaction plus preheat zone is thinner than the Kolmogorov scale. So which means it is delta L less than eta. So transport of mass and heat between the reaction zone and the preheat zone is by molecular mixing, and as a good approximation, the local flame propagates at laminar speed and the thickness of the flame is laminar. So if you look at the Kolmogorov scale by m dot reaction all layers, this is U eta by delta A d by del A square, which is del L by eta U eta by d, which is del L by eta less than 1. Now, if we go to thin reaction zone, their Karlovich number is tau c by tau eta del L by eta, which is a square. So, Karlovich number lies between 1 and 100. So, here the same thing, if we look at it, we can see one zone here and one zone here. This is our unburned, this is burned. So, the eddies are kind of took that. Here the reaction pockets may not pass the inner layer of the reaction zone. So, here one can say that m dot Kolmogorov by m dot reaction all layers is u eta by del by omega, which is u eta del L by d by del L square. So, which is essentially del L by eta, u eta by eta. So, del L by eta greater than 1, and the other round Kolmogorov by m dot reactions all layer, you can say u eta by del L by SL by del inner layer, which is del inner layer by eta, u eta by eta d, which is del inner layer by eta, 0.1 del L by eta. So, which is 0.1 Karlovich number to the power half, which is less than 1. So, different resume you see different kind of. Now, if you go to distributed reaction zone, here Karlovich number is essentially greater than 100, and the same flame front if I see, then there would be unburnt, burnt, and this would be a pocket where you can have a large vortices. This will move. So, reactant pockets may pass the reaction zone without full consumption. So, in that case the Kolmogorov by m dot reaction would be del L by eta, u eta by d, which is del L by eta greater than 1, or m dot Kolmogorov reaction would be del inner layer by eta, which is 0.1 del L by eta, 0.1 Karlovich number half greater than 1. So, this is what happens in the reaction zone. Now, if you, this is TPF is the turbulent premixed flame. So, this propagates due to heat transfer to preheat zone to heat up the fuel layer to above crossover temperature, and fuel layer mass transfer to the reaction zone to provide fuel layer. So, transport of mass and heat between reaction zone and the preheat zone can be different for laminar premixed flame depending on the thickness of the zone. So, this is now we have seen the flame speed. So, this is our fresh gas, this is burned gas, this is an isosurface of the flame front. So, this is a time instant t, this is time instant. So, C is the progress variable and Cf is the iso level of the progress variable at maximum reaction rate. So, this is the equation, and absolute speed would be w dot n. So, this is how the velocity vector, this SD would be acting in this direction, this is u dt and this is w dt, and SD would be w minus n, this is displacement speed. So, one is absolute speed, one is displacement speed, and delta n is the unit normal vector, which is calculated like delta c by mod of delta c. So, apart from that, you can see now if I start with this equation where del c by del t w dot del c 0, now I use the unit normal vector, then I write this. Then from here I can get absolute speed is w dot n, which is 1 by del c by del t, and then that will give me the displacement speed between these, which is 1 by magnitude of del c del t of u delta c. Now, you can find these things, then we can find out the relationship between the displacement speed and the species equation using this information. So, we will stop here today and continue the discussion in the next lecture.